In this video, I'll go over Dijkstra's shortest path algorithm. The algorithm receives the starting node as an input, and then it finds the shortest path from the starting node to any other node in the graph. The algorithm uses a minimum heap structure to keep track of things, basically. So let's go over this algorithm, apply it to the graph that you see in the picture. At the beginning, for each vertex in the graph, and this graph has 4 vertices basically, for each of those vertices you are going to set the distance of that vertex to infinity, and this is how it's done right here. That represents the distance of vertex A from the starting node, and in this case the starting node is also vertex A, and we're going to initialize its distance from the starting node to infinity for all the vertices in the graph. And also each node in the graph keeps track of its predecessor node. So if you have the shortest path, the predecessor node helps you reconstruct the shortest path, basically. So each node keeps track of that predecessor path. Initially, they're all set to 0 or null, if you want to call it. Right? So that's the initialization that's done once at the beginning of the algorithm, basically. And then what you do, you push all of these nodes A, B, C, and D into this unvisited queue, which is really a minimum heap. So there is the unvisited queue, all the nodes A, B, C, D, they're all in there. Right, so the algorithm initializes this way. Then the for loop is over there, and then what you're going to do, you are going to go to the start vertex, in this case A, and set its distance to 0. So notice how this distance, which was initialized to infinity, now after this line of code, it is set to 0 now. So the distance of a starting node is 0. After that, you get into the while loop, and the rest of the algorithm basically works in this while loop. Now, while the unvisited queue is not empty, and it is not empty, there are 4 nodes in there, you are going to have the current vertex is equal to pop minimum kind of a vertex from this unvisited queue. Now, minimum pop min, basically it means the node with minimum distance. And in this case, among these 4 nodes, we initialized the node A's distance to 0, which was the starting node, by the way. So that is going to be popped, and the current V is going to be A. That's basically the starting node, basically. Right. So we pop that, and then we go through this for loop. For each vertex adjacent to A, for each vertex adjacent to A, what are the vertices adjacent to A? It is B and C. So what are we going to do with those adjacent vertices? You're going to introduce this variable edge weight. Edge weight is equal to weight of edge from current V, weight of the edge from A to this adjacent node. Let's start with adjacent node B. That's adjacent to A. So in this case, edge weight will be 3. That's what edge weight will be in our case. It is the weight of the edge that connects current V to the adjacent node, basically. That's 3. And then we have this alternative path distance, which is equal to current V distance. Current V is A. What is its distance? It is 0, right? That is 0 plus edge weight of 3. That gives us 3. So this alternative path value is really 3. And then you move on to this conditional statement. If this alternative path distance, which is 3, is less than adjacent a node, which in this case is B distance. Adjacent node's distance is infinity. So it's saying that if this 3 is less than infinity, which is definitely the case, then you are going to set the adjacent distance, B's distance, to this alternative distance, which will be 3. And then the predecessor pointer of B is going to be current V. So this predecessor, instead of being 0, is going to be A. Right? So basically that means that B is reached from A, and the cost of reaching it is 3. And that 3 means the distance of B from starting node A. Now we do the same thing for the other adjacent node to A. What is the other adjacent node to A? The other adjacent node to A is C. So we go through exactly the same thing. What is edge weight? Edge weight is 7, right? Weight of the edge from current V, which is A, to the adjacent node, which is C. That's 7. And then what is the alternative path distance? It's current V distance. The current vertex is A, distance is 0, plus edge weight of 7, which is 7. Now, is this new distance 7 less than the distance of C, which was infinity? Yes, that's the case. So what do? You update the distance of C to this alternative value. So this will be 7. And then also update the predecessor node to A in this case. So that takes care of this, basically the while loop. So we basically popped the minimum distance node from the heap, which was A, with distance of 0, and then updated its adjacent nodes. So then what we have here is this next figure basically. There's node A, we updated node B, distance of it is 3, predecessor node is A, C, distance of it is 7, predecessor node is A basically. Now we go to the top of the loop. Is the unvisited queue is not empty? No, it's not empty. We got 3 nodes in there. Pop the minimum. So which one of these nodes have the minimum distance, the smallest distance or minimum distance, except between B, C, and D, of course. B, C, and D, of course. It is 3. So B is our current vertex now. It's right here. We analyze this. We look at these 3 nodes. Which one has the smallest distance? It's node B. We basically make that the current vertex. And C and D are left in the unvisited queue. So you're right here. You're right here, in fact. We popped it, and the current node is B basically. Now for each vertex adjacent to B, what are the nodes adjacent to B? Adjacent to B would be, these are directed graph, right? So this is C and D. These are the adjacent nodes basically. Now let's go after specifically the adjacent node D here, right? What is the edge weight? Edge weight is 1. Right? And then what is the alternative path distance? It will be current V distance. That is the distance of B. The distance of B is 3. So that's 3 plus the edge weight of 1. So 3 plus 1, that gives you 4. And then you go through the conditional statement. Is this 4 less than the distance of D? The distance of D was infinity. Probably I had the pictures off a little bit. The distance of D was infinity, and now we update it to 4. There it is. And then also update the parent pointer, which will be B, from B. Right? Now, what about the other adjacent node to B? The other node is C that we have in there. So let me clean this up as well. So let's go and take a look at node C and see whether this is updated. For node C, we have here the let's say edge weight. The edge weight is 5, as you can see there, right? And then the alternative path will be current V distance of V, which is 3, plus edge weight of 5, that's equal to 8. Now, is 8 less than the value of distance of C? Distance of C is 7. Is 8 less than 7? No. So we don't update anything related to C. So only D was updated in this case. All right, and then we are done with this loop again. We go back to the top of the loop, and then is the queue or heap empty? It is not. What is the minimum between C and D? Minimum between C and D is D. So D becomes the current node. C stays in the queue. And then for each vertex adjacent to D, what are the nodes adjacent to D? The only one that's adjacent and you can reach it would be C. C is adjacent to D. You got to follow the directions, right? B is not adjacent because you can't reach B from D. You can come from B to D, but not from D to B. So adjacent to D is only C. Can we update the value of C? Let's see. Let me just clean up this information once again. Now, what is the edge weight? The edge weight right here is 2. That's the edge weight. Now, what is current V's distance? Current V's distance is 4. 4 plus 2 is equal to 6. Is 6 less than the value of 7 that was the distance of C? Yes, 6 is less than 7, so C's distance is updated to 6. Right? And then the only item left in the queue is C. We update or pop C from the queue. So current vertex will be C. The only adjacent node to C is D. You can see the arrow there. The only one is D. Can we update the value of D? Well, let's see. The edge value or edge weight is 9. The alternative path value or distance will be 6 plus 9, which is 15, and that is not smaller than 4. So D will not be updated. And then, so this while loop again is finished. You go back to the top of the loop. Queue is empty, and we are done basically. Right? And if let me see that I can go to the next page. As I go to the next page, so this is it. This is the final result that we have after going through the Dijkstra's algorithm. Now, if you want to find the shortest path from the starting node A to, let's say, node C, all you need to do is to go to node C, right? First of all, the distance will be 6. That's the shortest path from A to C. Now, what is that path? Well, you have to, from C, you have to go to D. So from C, you have to go to D. I'll work backwards. From C, you have to go to D, right? That's the node, parent node or predecessor node. And from D, you have to go to B, predecessor node. And from B, you have to go to A, which is the predecessor node. So the path A, B, D, C has the value 3, plus 1 is 4, plus 2 is 6, is the cheapest way to go from A to C, the shortest path.